Right. All right. Hello, everybody. Got the standard thinning out of the class now. Have more people hopefully probably still watching online videos of the class. But today is another exciting topic. It's actually the last big model family of sort of the basic models, which we can then extend and combine in later lectures, namely tree recursive neural networks, or tree RNNs, or used to be just RNNs, but then recurrent neural networks kind of took over the main default abbreviation, and constituency parsing. We've already talked about dependency parsing. Today we'll talk about another linguistic formalism, namely constituency parsing, which we've already covered a little bit, but we didn't really give you a method on how to actually find these kinds of parses before. So we'll motivate both of them a little bit, talk about how we do structured prediction with these simple tree RNNs, look at how we train them, have a few equations, but we can kind of go over them fairly quickly, and then we'll look at more complex compositional kinds of units in these tree-structured recursive neural networks. Before we get into any of the content, a couple of announcements and reminders. So it's really time to gear up on your GPU knowledge, set up your Azures, your Docker containers, and everything. Also, the final project discussions are super important, are pretty much the most important thing you can now do for the class. So really, please do meet with us. You can use all the normal office hours for your default final project questions. And then my office hours will also be today after class again. We'll take as long as we need to answer all the questions. If you are assigned to me or have done a default final project or your own final project, then your default is that you're assigned to me, so you have to come every week now. It's part of your grade, so make sure you don't miss your office hours and have weekly updates with results for everything. Also, there's no other feedback mechanism for your projects other than the actual project advice office hours. That's what they're for. They'll be as long as needed. If they're too many and we need more advice, we'll do them every Tuesday and Thursday. But yeah, there's nothing on grade scope. This is the project advice office hour is where it's at. All right, any questions about organizational class issues? Yep.
So is that like starting today I have to go? Or
I've really set this for about the last 3 weeks that you have to come. So you should have come the last 3 weeks. I don't know your face, so you have not come. So yes, today is at the very least, yes, also. Please come to Project Advice Office Hour. All right. Awesome. All right, so we've covered a bunch of different models, and in some ways, linguistic models for trying to understand the structure of language can be kind of captured in two very far extremes. On the one side, you just have bag of words models, where you really don't care about the structure of a sentence or document. You just basically jumble up the order and sum up whatever you know about each of the words. And that works surprisingly well the longer your documents are. If you just try to do sentiment classification and you just want to know if this overall document is positive or negative, it turns out it's often good enough to just capture that amazing is somewhere in that document. You don't need to know that much else about a document. On the other side, you might want to really understand the complexity and the structure of a sentence. And there you can go into very complex linguistic formalisms where you assign a lot of different structure to each word, and each word might be a function that acts on other words. It might require a subject. And then you can look at agreement. If, for instance, in English, there are very few agreement requirements between a verb and a subject. So he runs versus they run, or I run. So the verb has to be an agreement in its suffix, in this case, or in general in its conjugation to the subject. And you might want to capture all of that in a sentence and really identify, is this a grammatical sentence, yes or no? And really try to extract from that structure other information you might want to know. For instance, is this used as a tool? Give me all the things that were used as tools by an agent that was also acting in a certain location. right? If you want to have these kinds of complex structures and you want to extract that from sentences, then you might want to go into very complex models. And further, you might just be interested in linguistics itself and not do NLP for the sake of doing something useful for actual end users, but you want to use NLP just to understand language better. And in those cases and others, it might be helpful to really understand the structure of language. And as soon as you study that structure, you'll realize that we want to go beyond just the meaning of these single words, which we've covered very, very well with word vectors, and we motivated those compared to like a thesaurus, like WordNet, and so on. And you'll realize, well, what if you want to capture the meaning of these larger units? So let's say you wanted, for instance, understand that these following two sentences are quite similar in their meaning. The snowboarder is leaping over mogul, and a person on a snowboard jumps into the air. Now, if you just looked at single word vectors, a snowboarder might be somewhat close to snowboard, but really one is a person, the other one is some kind of tool and an inanimate object, so they're not that similar. And in some ways, you might think snowboard is more similar to skis than it is to a person that actually snowboards. But the combination of a person on a snowboard is quite equivalent to a snowboarder. And so what's clear is that people, and ideally AI systems also, interpret the meaning of larger text units, may it be single entities or descriptive terms or entire facts that consist of longer descriptions, arguments, or even entire storylines, in terms of semantic composition of these smaller units. We combine somehow a person on the word a and a snowboard to combine overall to the meaning of a snowboarder. And compositionality is not just a concept that exists in language, it clearly exists a lot in a lot of other places on Earth. So this is a Ducati engine, one of the simpler ones. And there also we compose smaller pieces that are not that useful in and of themselves and combine them to do something much more meaningful, namely propel you forward very quickly. And we have this in man-made structure, but we also have compositionality even if it wasn't for humans trying to generate something, or humans making up a language, or humans building an engine. We have compositionality also in the visual world, where images overall are composed of smaller parts. And people might be seen as being composed of smaller parts, like limbs and eyes and noses and so on. And we might see a church as being composed of a roof and windows and a facade and so on. So in some ways, language understanding and in general, the field of AI requires us to be able to understand bigger things from its parts. And it's actually something that is we'll make some progress towards in this class, but it's still a major issue that we cannot do very well yet. It's very hard for most AI systems to be able to generalize from the little training data that they usually have for specific pieces and then really understand what those pieces mean. And a good test of real understanding is often if you can use a concept you've learned on something else and combine it with other concepts you've learned to build new, larger, more complex things. And the answer in most of AI is usually no. People have found various ways, and we'll cover some of those today, that make progress on this, but it's a major issue. And this compositionality touches in particular in language the question of recursivity or recursion in that we can compose language from words, and it turns out that a lot of other animals have various forms of language as well. And they also have simple words. And you can see this language faculty in really all kinds of different species, and sometimes it's verbal communication, there's also nonverbal communication. But what makes human language the most unique is our level of recursion, how complex of a sentence we can build that still makes sense to one another compared to what animals do. Animals can say hungry also, or food, or danger, and things like that. And maybe they combine and say danger and then point to something and from monkeys, but they can't really form complex kinds of sentences as far as we know and as far as people have studied their language. There's some cases where Some people think that maybe ravens have in some of their songs some recursive structure, but it's still a little bit debated. And if it is, that does exist, it's very, very simple. So you might really ask the question, do we have to structure language and think of it through recursive ideas and through recursion at all? Because so far we've gotten pretty far in just seeing a structure that goes from left to right, and builds a hidden vector and some LSTM model, and that got us pretty far. And so you could also argue, and this is a big argument in psychology and cognitive neuroscience and other places, whether the human brain really parses language in some kind of recursive fashion, or if we really just go from left to right and we keep some memory that we update. But what's clear is that recursion is very natural for describing human language from a linguistic standpoint. So you have sentences such as, and this is the maximum of recursion that many people can parse too in terms of noun phrases, but the man from the company that you spoke with about the project yesterday. So this is basically a noun phrase that is inside a noun phrase that is inside another noun phrase. And when you just want to formally describe such a sentence, recursion is a very obvious way of doing it. And now in many cases, the grammar formalisms that people come up with allow for much, much deeper recursion that people usually cannot parse themselves anymore, and that kind of overshoots that idea. But clearly, there's usefulness in describing recursion that way. And we've already covered this example of a dependency parse where we used the idea of recursion. We didn't make a big fuss about it at the time, but here we also have a spoon, which is a noun phrase, and that attaches in some cases to a verb phrase, but in other cases to another noun phrase. And so having this recursive tree structure as a formalism to describe that sentence helped us immediately understand what kind of meaning we want to convey overall with the sentence. And for people, this is very intuitive that with a spoon changed here the verb phrase and the way you eat the spaghetti, whereas with meat changed what kind of spaghetti you're eating. Now, there are two other reasons you might think of recursion as useful. And that is when it is clearly helpful for some tasks to refer to longer phrases that you've seen in previous contexts or in a previous sentence. So if you have, for instance, the sentence, John and Jane went to a big festival, they enjoyed the trip and the music there. And now you want to have a specific reference and understand what does they refer to. And they cannot just refer to a single state that ends at a specific point in time, but it really refers to John and Jane, that entire phrase. And in a constituency parse, that would be one node in a tree like this. It would be one particular noun phrase. The trip refers to a longer phrase, namely went to a big festival, and there refers to the big festival. So those are all nodes in a constituency parse tree that, if we have it, we can refer to directly. And in some cases also, we'll find out which cases those are in a little bit. We just have very practical problems, and having these grammatical tree structures is just a powerful prior and will give us better performance as well. So that leads us to the question, how should we formulate this? How should we build a meaning representation for phrases? And there are a lot of ways we can do this in traditional linguistics. Here, we'll actually use similar ideas to what we had in word vectors, and that is to also map phrases into the same size vector space. So if we had the country of my birth and the place where I was born, then in some ideal vector space mapping, those would be close by in the resulting vector space of multi-word units. And if you just were to average those, they might not be the same, but here in both cases, this is essentially some kind of location, and even the place where I was born, you would hope would be more likely, not a street name or a hospital number or something, but in most cases people would think of it as a country or at least a city. So we would ideally hope that they get closely mapped to other country names, for instance, even though they're multi-word units. Any questions around the idea of vector spaces for multi-word units? Mm-hmm.
On the previous slide, you were saying that the constituency model will help with like co-reference problems if they refer to something. But with RNN, we can also define like a span as what they're referring to. Is that how it would?
So yeah, good question. So here I motivated recursion also in terms of being able to refer to a specific node in a tree that covers multiple words. But you could say that you can also describe all of these here in terms of just a span. Like start at word 1 and end at word 3, or in this case, you know, John and Jane, yeah, 1 to 3. But then, of course, if you have a span from, and we'll get to that in a second, a recurrent neural network, then the nodes in that network will represent everything from the left to the right. So they will not just represent that phrase, they'll actually represent the context up until that state. So if you wanted a representation for just this phrase, a recurrent neural network wouldn't do that for you. I'll go through that example in a second. So the question is how we should map these phrases into a vector space. And in this case, the idea would be to use that principle of compositionality. Not just go from left to right, but go in an order that makes sense grammatically and based on the meaning. And so the meaning vector overall of a sentence will be determined by 1, the meanings of its words, the word vectors, and 2, the rules that are used to combine them. So we might say my birth is a proper noun phrase. And we have here possessive determiner my. Then we have the country, which is a proper noun phrase. Of my birth is a prepositional phrase. And then we combine all of that into one final vector representation. And in this lecture, we'll learn about models that can do both together. They learn the grammatical structure, and they will give us a representation. So how would this work? How would we use a constituency sentence parser to actually get a final vector out? Well, here's another example. The cat sat on the mat. Very simple example. In standard syntactic parsing would just give discrete categories to all of these representations. So the cat is a noun phrase, so it's the mat, on the mat, sat on the mat is a verb phrase, and overall this is a sentence, and the output of parsing, constituency parsing, would be just this discrete tree structure. In our case, we'll also want to have a semantic and syntactic vector representation of all the nodes, so we can have the advantages of both. We have discrete tree structures as well as continuous vectors that might give us access to similarity metrics and things like that. Whereas just knowing that this is a sentence wouldn't allow us to ask what are similar sentences in the corpus. What are similar sentences in the corpus? And now here's partly the answer to your question. So the main difference between recurrent and recursive neural networks is that one just go from left to right, and one will decide how to compose the meaning and in which order we'll compose the meaning, which will allow us to have representations for just a particular phrase in isolation without the overall context. Which means we also require this tree structure, which is one of the major downsides of this model family. But it does allow us to have these isolated things without any prefix context. And also, it might allow you to not just focus on the last couple of words. Sometimes the very important bits are in the beginning, and as you go from left to right, the final vector representation here will look much more like the last couple of words than the first. But of course, this representation will depend very much on the parse tree structure, and if you make a mistake there, you might also have issues. So there's always a trade-off in all of these models. Yeah.
What do you get from a tree structure you don't just get from a dense and connected?
What do you get from a tree structure that you don't get from a dense representation? What do you mean by dense representation?
Where you have a bunch of skip connections where every level, every word then is going to be.
Okay, so what do you get from a tree structure compared to having a bunch of skip connections? So the skip connections would eventually grow too much, right? You'd have like quadratically many, so that's one issue. Two, a lot of skip connections would also not give you representations of specific phrases in isolation. And then three, a lot of times when you want to identify, for instance, which drug interacts with which protein or might have a certain side effect, if you get a tree structure like this, you immediately can say, all right, I want all the things that are in this part of the tree, then there's a verb, and then there's this protein as an object, and then you can immediately extract some structure, even though you don't have training data for that particular interaction, but you have training data from other parse trees. You just parse the original sentence, and you can come up with a very simple rule to extract certain kinds of information. And then there are a bunch of other reasons. One is you might just want to understand the language in and of itself for linguistics, like linguistic studies, and a bunch of others. But yeah, those are some of the important ones.
How would you implement this kind of recursive tree structure?
All right, that's a great question for the next slide. So how do we actually get a recursive neural network structure? How do we use this model to come up with the tree? Well, the first thing we're going to define is the standard neural network. And now at each time of application of this neural network, we have two inputs, namely the two child vectors. And we'll have two outputs, another vector representation, the hidden state, and a score. Often the score is coming directly from that hidden state. And in our case of parsing, we're going to define that score to be a measure of how plausible the new node would be as an actual grammatical phrase. And that's another good example. Like when we sum up all these scores, the tree structure will often tell us how grammatical of a sentence this is. It sort of falls out of the model. And so to define the simplest recursive neural network, we actually will have very similar things to what we've had before. We basically just have a standard single layer neural network that computes the parent vector p based on a child vector c1 and another child vector c2. And then we compute a score with a simple inner product. So nothing new in terms of that math. But the trick now is that we'll actually use that same w parameter at every node of the tree, just like before we used the same w at every time step. And you might ask also, and you might observe, that a tree structure is actually just a more general formulation to a chain. Every chain is essentially also a tree. So you could write, if you have a recurrent neural network, and you go here, then you go here, and then you go here. Right? This is, in some simple form, a recurrent neural network with some zero state. And that is essentially, you just lift those up, and it's exactly the same if you write this as a tree structure. Right? So chains in graph theory are just special types of trees that are branching in just one direction. So in that sense, recursive neural networks are just a more general model family, and recurrent neural networks are a special case of those networks that are restricted to chains and not more generally trees. And then trees are just special cases of directed acyclic graphs, and eventually you just get general graphs. And those will have very funky properties because you keep having to go in loops. You can't really converge. So very few people work on those. There are some people in other areas of deep learning that work on general graphs, but they're insanely hard to train. Just think about all the issues that we have with recurrent neural networks already in exploding gradients. You'd have those even in forward propagation, not just in backward propagation, because you might go into loops and things like that. So most people focus on directed acyclic graphs as the maximum complexity of graphs of neural networks that we look at. And trees are just more general graph structures than chains, and chains are special cases. All right, so this is the main equation. So how are we going to use these two equations to actually build up a tree structure? It's going to be very simple. We're just going to look at a bunch of possible combinations, and in the simplest form, we'll greedily build up this tree. So we'll start with looking at the first two words. For now, we'll assume that only neighboring nodes and neighboring phrases and neighboring words and phrases can combine. You can't combine with anything that's further away, and that's fine for pretty much all parsing algorithms. So we pipe these two potential child candidates vectors, and again, in all these pictures, they're two-dimensional. They'll be proper word-to-vec vectors with like 50 or 100 dimensions. We'll pipe them, we'll concatenate them, pipe them through a single layer neural network, get the hidden layer out, and from that hidden layer compute a score. We would assume that the cat is a pretty reasonable, very simple noun phrase, gets a very large score. Then we're going to use that same exact neural network and pipe cat sat, concatenate it into it, sat on the, and the mat. And then in the simplest form of this algorithm, what we'll do is just merge the two nodes that get the largest score, which in this case is the cat. So we're just going to take the hidden vector of that neural network, and we'll assume that is now the representation for the combination of those two words. And then, and this is why we call it recursive, we're going to apply the output of that network as an input to that exact same network again. To compute another candidate, namely, should the cat as a phrase be combined with sat? The cat sat is actually not an unreasonable phrase, right? And so it would get a reasonably high score. But we'll, in a greedy fashion of this parsing algorithm, we'll just take the next highest score, which will be the mat. And so we'll merge the mat, and now again there's a new combination that the network has not yet seen and looked at, and that will be on the mat as a new phrase, which is a very nice, very simple prepositional phrase. So we would assume after the model is trained, it would also get a high score. And we'll basically keep building up the tree in this fashion. Any questions around the simplest form of this algorithm? Yeah?
Is it reasonable to pre-train some phrases like the cat, the mat, so not to compute them every time?
Is it reasonable to compute what again?
I mean, in this case, we compute the result for the cat, and now rerun our training. But is it reasonable to have those common phrases already in the database or somewhere?
Oh, interesting. So here, yeah, if for each sentence we recompute the pairs, you could try to think of a pre-cached, pre-trained model that if your word vectors weren't changing, which they might sometimes, then this is not useful. But if your word vectors don't change and you have certain bigrams that are very, very common, you could just pre-compute that hidden state and just look it up. Yeah, that's possible. It's unclear how much it would help. Like now you have to, there are a lot of potential bigrams and potential trigrams and so on. But I could see certain speed memory trade-off where that's a sensible thing to do. Yeah.
So for this case, the representation of a sentence is just a tree of vectors, right?
That's correct. For this case, the representation of the sentence, as we've described it so far, is just this tree structure and a vector at every node representing all the words underneath it.
So if two sentences are similar, they should have similar structure and also similar values.
That's right. If we want to have, in this final vector representation, two sentences to be similar, they actually have to have not just similar words, but also similar tree structures. Or, and this is kind of an interesting question, could they have different tree structures and different words and still get a similar vector representation out? Ideally, they would. In practice, that doesn't always happen. But there's some, and we'll get to some examples, there's some what we might call semantic invariance, or syntactic invariance, where different syntactic structures, slightly different words, will actually give you very similar vector representations. Yeah.
So before we have this 100-dimensional space where you have to fit an embedding of every single word vector, right? But now this space also has to fit the representation of every single bigram, trigram, etc.
Right.
Does the space get a little crowded? So that you can't distinguish things very well?
It's a great question. Does this space get crowded? In fact, this paper was actually one of my papers in 2010. It was one of the first papers of deep learning at a major NLP conference where we used neural network as a term, and reviewers would actually reject the very first submission because we used neural networks in an NLP conference, and that was totally not hip to do at the time. And so, and one very heated debate became about, like, should you ever actually squeeze variable length words, variable length phrases into a single fixed vector dimension? And it infuriated some linguistically minded researchers in the NLP community. You can do some very simple back of the envelope calculations of, like, thinking the longest sentence of the English language is maybe 40, 50 words or so, and you have a vocabulary of maybe 40,000 words to capture most of them. So you have a pretty simple 40,000 to the power of 40 many combinations of English sentences. And 2 to the power of 500 is much, much larger than that. So even if you were to try to memorize all words with this vector representation, if it was 500 dimensional, and it was only a binary representation, which it's not, it's all real numbers, you could literally memorize all sentences in the English language. Now, that is just one argument to bring up for why it's fine to have 100, 200, 500 dimensional vectors to capture all of the complexity. Now, of course, just memorizing it in a binary vector is not going to give you the kinds of properties we would want from these, which is like semantic similarities and so on, but it shows you that it's probably enough. The space is large enough to have that kind of capacity, largely because humans don't generate sentences that are more than 100 words. There's some German authors that like to have sentences that go over half a page or a full page, but it's pretty uncommon, and most people kind of aren't able to parse those sentences themselves either anymore. Great question. All right, so now how do we actually train this? So this was a inference procedure where we assume we have a trained network that's giving us these scores. How do we actually get the scores? And the way we're going to optimize this model is actually a generally useful mechanism, which we'll define in the next slide. But first, we'll just define the overall score for a sentence X and a tree structure Y to go through all the nodes in that tree structure Y and just summing up all the scores at each node. So very simple summing of all the different nodes, and that will define the overall score. It's an unnormalized real number for that sentence. The higher the score, the more we would assume this is a reasonably syntactic, grammatical kind of tree structure and sentence. Now we'll train this with a max margin objective, and it makes sense to walk through this kind of slowly. So we'll assume we have for each sentence xi in our training data set, a ground truth sentence yi. So we assume for that language, we know for several tens of thousands or hundreds of thousands of sentences, what the right tree structure should be. So it's a supervised structure prediction problem. And then we're going to ask our model to come up with the largest scoring tree, so of all possible trees that we have over xi. And it turns out they're actually Catalan many possible tree structures. And if you don't know Catalan numbers, it's a really fun fact and a good question, good Wikipedia article to look up. So we won't actually go through hyper-exponentially many possible trees. We'll have some clever ways of restricting the set. But in the algorithm, you could assume for now we have all possible tree structures that you could build from a sentence xi. And we'll select the one that gets the largest score. And then we're going to add also a loss here, or a penalty term for our margin that will basically compare how incorrect this sentence, this tree structure is compared to our ground truth tree structure. So if we have, for instance, multiple wrong decisions in our parse tree, the parse tree is quite different from the ground truth tree, we would actually give a bonus to this tree. And the reason we're doing this is that we actually want to encourage the model to make mistakes in the beginning. And once it gets the right tree, to actually have, so once y actually here it becomes yi, then this term will be 0. There's no more penalty, no more additional bonus given to a wrong tree, and then you have just s of xi yi minus s of xi yi, and you can ignore that tree. And you can then also know that the next best tree will actually be at least this delta term worse in its score than the correct tree. And that's where the margin comes in. The margin will be larger and larger between the correct tree and more incorrect trees, because we have this additional delta penalty term. Does that make sense? Yeah.
So the ground truth trees also have scores on each node?
The ground truth trees will, in the beginning, have everything has a score because we can pipe it through the currently untrained, in the beginning, recurrent neural network. And so in the beginning, so we want to maximize this overall. And so that means we want to maximize here the score for the correct one, and want to, because there's minus here, minimize the score for the next highest scoring but incorrect tree.
So when you're collecting the data, you just need the tree structure. And then
That's
the
right.
scores will be assigned by the untrained network.
That's correct. The trees, the network will always assign you the score, but at training time, you do need to have a ground truth tree yi. Yeah.
Is it possible to get a negative value for this loss if, say, your model assigns a very high score to an incorrect tree?
Is it possible to get a negative score for this loss? Overall, yes. In fact, the scores here are completely unnormalized scores, and the best tree might be minus 100. And the next worst tree is minus 200 or minus 102 or something like that. Yeah.
What is our target? The similarity between two words?
What is our target? The similarity between two words. Right now, for this objective function, the target is only to predict the right tree structure. And it penalizes every time you have some kind of difference in the spans between the ground truth tree yi and your currently highest scoring tree y, you're going to add this penalty term, which then will choose this tree y to be lowering its scores, right? Like intuitively, what happens in the beginning is you try to maximize the correct tree. So you take your currently untrained network, you do feed-forward propagation through this existing tree structure. Then you'll try to find some clever way to find the currently highest scoring tree. And as long as those are not exactly the same, you will then try to minimize the scores of that tree. So you keep pushing up scores for correct trees, and you keep trying to lower scores for incorrect trees because you do minus the max here. And this max margin formulation is actually very useful in a lot of different machine learning problems. There's also the idea behind support vector machines and lots of other areas. And you can also have support vector machines give you structured prediction, and then you'll have these kinds of penalizing terms delta. Yeah?
So if your tree structure y is really different from the truth y hat, the delta there will be large, and it will push the really big, the one with the really big difference to be the maximum one, right?
So if your currently highest scoring tree is very different to this tree, indeed, it will basically try to lower all the scores of that currently highly scoring but incorrect tree. But it doesn't do it any differently. You have the scores and you try to lower them until the correct tree yi is either the same here or is at least in some cases better than a certain margin to the next incorrect tree.
Oh, this is the objective, not the loss function.
Sorry, objective and loss functions are the same thing.
Oh, they are. But if you're minimizing this,
Oh, you're maximizing it.
Oh.
Yeah. Sorry, this is like a terminology thing. You could call objective function, and we say we always maximize objective functions, and then when we call it loss and cost functions, we'll try to minimize it, but it doesn't. Yeah, we'll call it objective here. And yeah, it's very important that we're maximizing this. Yeah. Of course, you can flip the semantics and just say minimum is better. And anyway. All right, now instead of actually, I described how we find this AX here in a greedy fashion. So with this kind of way, where we just pick the highest scoring one. But just like in machine translation, we can actually have a beam where we keep around a couple of candidates for each of the decisions that we make, and then actually keep checking for all the variants in that beam to find the best one. And that will kind of look, for those of you familiar with traditional methods like this, like CKY parsing, but you can't ever find like a globally optimal tree with this method. So unless your beam is like so large it includes all possible tree structures, you can't really guarantee that you find the single best one. Now, in order to train this, we basically know all the things we need to know, especially since we understand flow graphs and TensorFlow. This kind of falls out quite easily. And you'll see these kinds of equations that you should be able to derive in general. So for standard neural networks, when we have just a single kind of input, no recurrence, we basically have here the delta computation to compute the error responsibility at each node. And then at each layer, we basically have an outer product between the delta and the activations of that layer. And that will be our final derivative. And now there are only three major differences of the standard backpropagation on a fixed neural network and recurrent, recursive, tree-structured kind of backpropagation or backpropagation through structure, which is actually, again, also a very general term. If you have, for instance, some kind of directed acyclic graph, like WordNet, and you want to propagate something through that graph, you can also use this kind of algorithm. And there are three main differences. One, and we'll just go through them, you basically have to sum the derivatives at all the nodes. They're technically the same W parameter that you have at each node, but it turns out you can kind of treat them almost as if they're different and then go through the math and you'll realize it's actually the same thing. So don't have to go through this. You can just kind of assume W here is a single variable, not a matrix, and kind of look at the derivative of W if you have such a very simple recursive function here that uses the W in both layers. And the derivative that you come up with is very similar, is exactly the same, to one where you take the derivative of W2, assuming W2 is different, and then of W1, assuming they're different, and in the end, you just kind of replace W2 with W, and it's the same thing. So you basically intuitively sum up all the derivatives that arrive in this flow graph that now is defined by the actual grammatical structure of the sentence. So one of the main issues of why this wasn't easy to do with TensorFlow is that TensorFlow wants to know the computational structure before it does backpropagation. But if you actually try to train this, the structure of the tree changes at each iteration. Each time you find a better score and combine certain words first, the tree structure changes dynamically. So when we built this, this was also many years before TensorFlow came out, we basically had to build our own dynamic graph evaluation algorithm for particular kinds of tree structures. And then intuitively, and this is kind of similar to what you've seen in recurrent neural networks where you go and one derivative goes to the previous hidden state and one goes to the word vector, you just kind of split your derivatives for each of the children. And then the last one is, and it's again not too different to recurrent neural networks, whatever comes forward during forward propagation will go backwards in backwards backprop, and then you basically have the total error message that arrives at each node in the tree coming from the score that you try to lower or increase at that node, as well as from the parent nodes. So it's essentially just a flow graph like we have in TensorFlow, but for tree structures. All right, now the code is actually so simple we can write out the entire code for backpropagation through structure in straightforward Python code. And this is actually something that I think is still useful to look at sometimes. Some people kind of become over-reliant on having a framework to do all the derivatives for them, and then they cannot build new models that don't have sort of preset default kind of primitives in them. and then are just completely at a loss. But hopefully at the end of this class, you can build new kinds of neural networks that nobody had ever thought of, and so the primitives don't exist in TensorFlow or PyTorch, and you could still write out what the derivatives should be using this. So forward propagation, you just assume you have for each node, this is a very simple sort of object-oriented structure here. Each node has a left child and a right child, and you assume in forward propagation you know what those are. You just stack them and have simple dot product between your matrix W of parameters. You add your bias, and in this case here we use rectified linear units as a nonlinearity. And then backpropagation through structure, basically at backprop you arrive at a certain node and you compute the derivatives for that particular softmax, for instance, that you might have at that node, or even simpler, just a single linear score. And then you basically, if you're at the very top, you add your errors from the parent node. Then you compute your delta based on f prime here, so in this equation. And then if you have a word vector, you might update your word vector. So the L here is L as our embedding matrix for all the word vectors, because you might want to have those as parameters as well. And if not, and this is kind of the main interesting bit here, is you basically first do, you first implement this equation where you just do the outer product between the delta messages that are coming in from this side and the activations of this node, which is essentially just the left and the right child concatenated again. Same for standard B, just the deltas that we've derived too. And then you're going to basically take and split the delta message into the left side and the right side for the two children. And then you call backpropagation on those nodes with those delta error messages. Yeah?
I don't think you can combine something like this with like a TensorFlow graph. So I think you have to write the entire thing by hand, right? Or what can we just simply say, for parts of my backprop, I can use my custom code.
So I think now TensorFlow has some dynamic evaluation of dynamic graphs, which where you lose some of the speed. And in general, if you want to move to more complex kinds of networks that are a little more researchy, my research group has found PyTorch to be generally much more helpful, where you can actually define arbitrary types of execution graphs at training and test time, and then it will figure out from the Python code where to go into which if statement and so on, and build up all the backpropagation just from having defined the forward propagation in more Python-looking code than what TensorFlow would allow. So PyTorch is the right kind of framework if you want to have more complex computational graphs like this. Yeah.
What is ER in this case? Is it like a node level loss?
What is ER?
In the red box, these are
Oh, sorry. So this is our error, our overall error of some kind of recursive tree structure. So loss or error or objective function. Yeah. Cool. All right. So now you can do backpropagation through general directed acyclic graphs, but also very clearly through binary tree structures. Things get a little more complicated once you have multiple children and so on, but it's fairly straightforward conceptually. All right, now so far I've only talked about the simplest kind of recursive neural network, or tree RNN. And in this tree RNN, we're actually asking a lot of a single matrix W to combine all kinds of words like prepositions and noun phrases, adjectives and nouns, determiners and nouns, verbs and nouns, and so on. And we keep asking the same W matrix to do all of those compositions. And that is asking a little too much. And so in some of the follow-up work in my PhD from a couple years ago, we actually extended this idea and used context-free grammars as the backbone to basically have more complex kinds of interactions. And so instead of having the same W matrix at each of the nodes, we actually allowed the different interactions to be computed based on different W matrices. And we took those from a simpler and very fast to compute, but not very accurate statistical model that just looked at counts of how often do certain words combine. And they would also give us the kinds of syntactic structures. So they would tell us, for instance, that this is a determiner, this is a noun, so this is a noun phrase. And so we can look, basically knowing that this is a determiner and this is a noun phrase, we have a different kind of vector composition matrix. And we called this a compositional vector grammar. It still had basically both of ideas of we have at each node now both a continuous vector as well as a discrete syntactic structure. We used probabilistic context-free grammars, which we're not going to go into much detail here. It's basically a very simple, very fast model to run, but in its simplest form, not very accurate. But it would allow us to basically prune unlikely candidates, so you don't have to do a lot of matrix vector products for things that are completely unrealistic kinds of grammatical structures. And it would also provide us these very core syntactic categories, like this is a noun phrase and a verb phrase and so on. There's actually a lot of work on extending PCFGs, and this is one of the lines of work. And kind of interesting historically, to me now it's kind of Trojan horse to get the NLP community to be excited about neural networks in some ways. At the time, they were struggling. Nobody wanted to use neural networks, but everybody loved syntactic tree structures. So it kind of combined the two and got people more excited about that model family in general. And having words being vectors and phrases being vectors and so on was all very new. And we got reasonable performance too. There are still some parsers that used several orders of magnitude more data and re-ranking and so on than us. But for other models that were very close, we actually were slightly more accurate, or in the case of these, or right around there. And what was interesting is we also got some very linguistically plausible analyses out of this model. And again, this is something that we would also encourage you. We actually just talked today in the TA meeting about a poster session where we have hundreds of posters all be the default final project. And that might not be very exciting depending on how exciting your posters are. So one of the things I would encourage you all to do is really come up with different visualizations of what your model actually does. What are the examples it's good at? What are the examples it's bad at? And then try to visualize the activation patterns and the units that actually activate for certain documents that you want to ask a question about. And those are very unlikely going to be all the same, and that might be some interesting analysis and way for you to differentiate, apart from, of course, being really high on the leaderboard, having very good accuracy, coming up with new interesting models. You can also think about how to speed up your models a lot. In many cases, we've now had models that take literally a week to train, and other people are able to make minor modifications, get very small decreases in accuracy, but train the whole thing in 6 hours. And so there are a lot of things you can do, and visualization is one of them. And so here are some examples for how different things combine. So if you combine, for instance, a noun phrase and a conjunction, like and, it basically looks mostly at the noun phrase. And what do I mean by mostly? Basically, these are visualizations of the weights of that W matrix. And remember, W is going to be multiplied with the left child here and then the right child there. And you might wonder where these diagonals, these block diagonal structures come from. And this is actually from the idea of initializing the W matrices this way. And what this does is essentially, actually, maybe you can figure out what this does. So if this is our W matrix and we initialize it this way, what would be the vector of the parent when you combined two children vectors, C1 and C2, that you concatenated here with this kind of initialized matrix? That's exactly right. They're averaged. So you have here an identity matrix times a half. So this first block gets multiplied and basically just multiplies all the numbers by a half, and then adds the second block of the second child matrix, is also just multiplied by a half. So you have a half times the two children vectors added, which is exactly average. And then here we have also a bias term, which we'll initialize to 0, and we'll add a little bit of random noise. And this is another trick that also helped some standard recurrent neural networks to work better later. And so intuitively here, when you say Jane and, the final vector will mostly look like Jane because the magnitudes of this block, which is the block that is multiplied with the left child, are much, much larger. And you basically have very small values closer to 0 for the second child. And this is true for a couple of other things. So for instance, it's kind of hard to read here, but adjective phrases and noun phrases, you have a little bit more on the noun phrase, but not as much. So the adjective here will tell you a lot too, if it's a full complex phrase. If you just have a single adjective and a noun phrase, you have a slightly higher magnitude on the noun phrase. And if it's a determiner, a noun phrase is most pronounced. So this is just the cat. That vector will look much, much more like cat than the. And what was kind of surprising and cool was this was the first time we took, or the field took a discrete structure, combined it with vectors, and then actually got some semantic similarities out that weren't just looking at word overlap. So here we basically took the top vector of a bunch of sentences from the Penn Tree Bank, this nice data set where a lot of people collected tree structures for, and basically looked at the top node of those sentences and then found nearest neighbors based on all the other parsed sentences. And these were some of the nicer examples that came out. Of course, when you have complex sentences, most of your nearest neighbors are not that similar because you just don't have, in a corpus of 40,000 words, that many sentences having a very same structure. Like if you looked at all the sentences I uttered during this class, you'll be hard-pressed to find 2 sentences or more than 2 or 3 sentences that are exactly the same or very, very similar, hopefully, unless I repeat myself too often. So here are the nearest neighbors for the sentence, all the figures are adjusted for seasonal variations. And this is a very financial kind of corpus, the Wall Street Journal. So you'll see that in these examples. The next closest sentence in the corpus to that one was all the numbers are adjusted for seasonal fluctuations. It's actually very, very similar, right? You basically just replaced figures and numbers and fluctuations and variations. So there's a very similar sentence that was found. And the next one was all the figures are adjusted to remove usual seasonal patterns. And that one is a little more interesting. You have, if you were to just go from left to right, then removing usual seasonal patterns is not that similar to adjusted for seasonal variations, for instance, if you looked at the last couple of words that were important. But this one basically figured out that to adjust, to remove usual seasonal patterns is similar to just adjusting for seasonal variations. And then Knight Ridder, some company, wouldn't comment on the offer. The nearest neighbor based on that hidden state of the top of the tree was Harsco, some other company declined to say what country placed the order, or the next nearest neighbor is Coastal, wouldn't disclose the terms. So you get a little bit more interesting kind of syntactic invariances from this model. And then again, there are a lot of examples where sales grew from some amount to some other amount, or rose or surged, and so on. And in some ways, those are not that interesting. And you'll also notice here some issue with actually antonyms, words and the meaning, words and other words that have the opposite meaning. So to grow and to rise actually have very similar word vectors. And you'll see this also when you train, when you don't train on sentiment, you just train on language modeling or word-to-vec, then oftentimes good and bad are actually very, very similar in their vector representations. Because intuitively, a lot of antonyms actually have similar kind of contexts. When you just look at short contexts, like 5 or 10 words from to the left and to the right. Like, I thought this movie was very good or bad, right? Like, or sales rose from this percentage to that percentage, or fell from this percentage to that percentage. So a lot of times you have similar context for antonyms, and that kind of issue of word vectors carries through to vectors that represent longer phrases. Now, the third variation that we'll cover is basically taking into account that some words and their interactions are actually different depending on what kinds of words you have. So for instance, very doesn't have much of a meaning in and of itself. But very actually acts more like an operator on the words that it's being combined with. So you might say, for instance, if good has some kind of vector representation, then very good should have a stronger vector representation in that general direction of good. So to take this idea, we essentially introduced a new composition function, and namely called it recursive matrix vector networks, or MVRNNs, where we basically assumed every word doesn't just have a vector association with it, but also a matrix associated with it. And whenever you combine two words, you will multiply the vector, the matrix of one with the vector of the other. So if you say very good, you'll actually take as input the vector here of B and multiply the matrix of A, capital A here, the vector of B. You do the same thing for B. Good will interact or act somehow on the very vector, and you get hidden representations from that, and then you basically take those and pipe them through the standard RNN. And then, of course, in backpropagation now, it's even less obvious how you do this. You basically have a similar kind of function for the matrices too. So each hidden state will also have a matrix that will act on the next combination, and you have to backpropagate not just into word vectors, but also into matrices. And this is also quite a reasonable thing if you were to, for instance, trying to come up with protein and drug interactions, and you wanted to have certain drugs have a strong interaction with certain representations of proteins. So a lot of these ideas carry forward into biology and outside of NLP. And this was the function we used, very simple linear function to compute the parent vector for the parent matrix for each node. Any questions about that different composition function? All right. Then we try to analyze, does this representational power actually give us better results on certain kinds of compositions that you might care about a lot? And so we looked at nonlinearity that you have in language, even for bigrams that we can analyze very, very carefully and actually have data sets for. And so what we did is we looked at a large corpus, very large corpus, larger than IMDb and others, of many millions of movie reviews. And we basically computed the bigram statistics for all kinds of bigrams. So in this very large, like millions and millions of movie reviews, how often would you see something like fairly sad? And basically in 1-star movie reviews, 2-star movie reviews, up to 10-star movie reviews. And just basically look at these normalized statistics. And you would assume, for instance, that unbelievably annoying would, as a bigram, appear very often in very negative movie reviews with very low stars, and very rarely ever in positive movie reviews, overall as a bigram. And then we asked the standard RNN and this matrix vector RNN to try to predict what these distributions are for examples that we didn't show it at training time. So here is an example where we actually had a training example. So the ground truth here for not sad was basically looking like this slightly noisier version. And all the other ones here are actually test examples. And so when you look at, for instance, fairly annoying, fairly acted as an attenuator. Whenever you have a word, this model learned that when you put fairly in front of that adjective, it would basically make everything a little smoother and not quite as peaked. So annoying, for instance, in general, would be more likely to appear at lower reviews, but fairly annoying, slightly smoother as its curve, whereas unbelievably, as an intensifier, would basically make certain predictions to be even stronger. So unbelievably annoying be even more likely to be negative and more often in negative reviews. And then not is interesting because it really has to flip the meaning entirely. And this is something we've noticed also in all kinds of neural networks, including LSTMs and others, is oftentimes will not have that strong of an effect on your hidden representation overall. And when you train it and you can look at actually, you find certain neurons where it might have a strong effect on, but overall in the hidden representation, it doesn't, depending on the size of your training data. And so not annoying here was actually where was one of the main areas where the standard recurrent neural network had a lot of trouble with and wasn't able to really flip that prediction over entirely. So not annoying in the RNN was still fairly annoying, fairly negative, and very peaked when it shouldn't have been. Whereas, and not awesome, likewise, the RNN still predicts a very likely appearance in very positive reviews where it should be much flatter, and likewise, it was sad. And now, there are actually some interesting things here that both models predict correctly. So here, as an intensifier, unbelievably annoying, very obviously very negative. Unbelievably awesome, very, very positive. But an unbelievably sad, and this is something that linguists are quite excited about, that this model correctly predict, you actually have this sort of U-shaped curve. And do you have any ideas of why you might see unbelievably sad, both predicted to be likely happening in very negative reviews as well as very positive reviews? Say again?
If the movie is a tragedy, it's supposed to be sad.
That's right. So if a movie is a tragedy, then it's supposed to be sad. And what does that tell us?
It's a good movie.
It's still a good movie. That's right. Titanic, tearjerker movies, things like that. Still very positive, even though the storyline is incredibly sad. But how do we get to this one?
It's sad.
It's very sad to do a movie this bad.
It's very sad.
To do a movie this bad.
That's right. It could be unbelievably sad to do such a bad movie, or the acting could be unbelievably sad, and so on, like an unbelievably sad attempt at doing something, and so on. So what's interesting is like these models were able to kind of predict that U-shaped effect after having seen other kinds of ambiguous adjectives in longer movie reviews that had it. All right, now the last application was actually in predicting semantic relationships. So this is something I mentioned these tree-structured models are quite good at. And basically, there's also a question we had, whether does it really help to have these large syntactic contexts convey semantic relationships. So what we tried to do here is basically mark a specific word in our input and try to identify its relationship to another word that we marked in the input as well. So if I say my apartment has a pretty large kitchen, then we wanted this model to identify that between apartment and kitchen, there's a component-whole relationship, where entity 2 here, the kitchen, is basically a component, and apartment is the whole. And again, this could be useful for extracting various other kinds of information afterwards. And we wanted to use that same kind of architecture, the MVRNN, to do this. And so we basically took the already existing parse tree, we marked it, and we just said we'll take the node in the tree structure that basically dominates, the lowest node in the tree that dominates both of those words. And then we had to classify both the direction, is it E1 or an E2, or E2 and E1. So because the order, of course, matters, and they're not symmetric kinds of relationships. And what we basically found is that when we just took this model, and this is based on a competition, and if you've ever taken part in a competition, you'll notice that people feature engineer a lot, and they have a lot of different components to try to win the competition. And so the best model here in that competition got an 82 F1 score, 82.2. And here are the features that back in the day they used to do really well on this task. And you'll see that kind of behavior still in a lot of Kaggle competitions where there is domain expertise and the data sets are quite small. So they use part-of-speech tags, WordNet classes, prefixes, and a variety of different kinds of prefix features that you could extract from a word. Then other kinds of morphological features, like is it all capitalized and so on, how long is the word. Then they use the dependency parser on top of that. And then extracted certain rules from the dependency parse. 11 classes, I'm not going to go into. Prop bank is another very large framework that basically classifies, in some cases actually, part of the relationships we try to extract here, but is another system, a complex SVM-based system with its own set of features to extract. Same with FrameNet. Then they used hundreds of gigabytes of Google Ngrams to try to extract more features and similar kinds of features to that. They used a paraphrase system that basically would take as input a sentence and generate paraphrases of that sentence. Yet another very large, complex machine learning model trained on a separate corpus. And TextRunner, which is also a semantic relationship classifier that actually included as its output two of the kinds of outputs that were tried to classify here, and eventually got to the system. And sadly, when we just use deep learning on these parse trees, we couldn't beat that system because there's so much external information that was just not actually captured in the corpus. So in the end, we also added 3 features to get the paper accepted, because you have to have state-of-the-art numbers often to get your papers accepted. And especially if people don't like your model family yet, and at the time people didn't like neural networks yet. And so we added 3 features and then beat that gigantic monster of a system. So hopefully that kind of showed you that tree structures can be helpful. Now in the next lecture I'll actually describe when to use what kinds of models and what the trade-offs are. What is interesting is this was a little bit pre-LSTM days, and so in the end a lot of LSTM models beat, with dropout and all the nice tricks that we have, beat a lot of these tree-structured models. But then former master's student, Kai Sheng, and I think now PhD student, actually combined ideas of LSTMs with tree structures and then got a little bit better again than the LSTMs and so on. It's a continuous kind of evolving race of which kind of model is best for which kind of task. But we lastly also applied these same kinds of models of recursive tree structures, actually pretty much unchanged from language parsing to image parsing, where we also tried to, again, understand scene images as small regions of an image that are then combining parts to larger objects, and basically try to understand how these different objects interact. And what was fun is it was exactly the same kind of structure prediction algorithm where you had little feature representations for smaller regions, and then you could learn to compose them and actually get some kind of knowledge about the structure of objects out. And that worked out reasonably well too, though at this point convolutional neural networks will probably do an even better job than this, though they might not give you much of the interpretability of the structure of the objects that you're parsing. All right, yeah, next lecture we'll actually combine all these different models. We've looked at window-based models, we looked at convolutional neural networks, recurrent neural networks, and recursive neural networks, all these different families. It turns out you can combine all these ideas with one another. You can have convolutional neural networks over tree structures. You can have convolutional neural networks combined with recurrent neural networks, have quasi-recurrent neural networks, and then eventually the biggest model family we'll get to in the last 2 weeks will be memory-based neural network models, where you can have memory states that are getting updated as you go over a document. And as we're combining them all, hopefully in the end you come out of the class and realize that it's still an evolving field, and you can kind of mix and match and play around creatively with all of these ideas.
So prefigs are really expensive to grade. So is there any hope for like the core resource languages on leveraging some of this?
Yeah, so one of the main problems with tree structures is actually that you cannot very easily parallelize them on a GPU. Right? GPUs are very good at taking a specific input vector or matrix and doing very large matrix multiplies in a very parallelized fashion. The problem is if every sentence has its own computational graph, you cannot do that. And that's one of the major downsides of having these tree structured networks. They're much more expensive to compute. You often have to use them on CPUs or do some very clever GPU engineering to make them as fast. Oh, sorry, for low resource languages. That's another issue. Oftentimes you want to basically just run something on another language that you don't have much training data for, and you can only run tree structured neural networks on languages that have some kind of tree bank, of which, like there are actually a lot of tree banks out there, like maybe 20 or 30 at least that are reasonably sized. But once you want to go below the top 20 or 30 most spoken languages, you're out of luck. And then you really have to use other models, though when you're that out of luck and there's that little training data for a tree bank, then it's also very likely you have very little training data generally for any of the other tasks you might want to do. And then deep learning in general might not be that great. All right, one more question.
Is there a practical limit to how deep these recurrent neural network trees can be?
So the recursive, it's a good mix-up. So recurrent chain structures, recursive general tree structures. Recurrent in some ways a special case, but some people in old neural network lingo actually saw recurrent as operating on any kind of graph. So in that old school way, it's the opposite, and one is a special case of the other. But the way currently people interpret recurrent as chain structured, it's a special case of recursive. There's no limit on how deep they are, but you can assume that the deeper the tree structures are, the harder it is for that top node to really capture all the content of the nodes underneath it. So you could use them for multiple sentences, but in some ways, the tree structure is very intuitive because of the recursion of language that we have in a single sentence. We have less of that kind of recursion in longer stories or between multiple sentences. So what we did often to combine them is we had tree structured networks for single sentences, and we had recurrent neural networks that just go as a sequence from left to right over those hidden states of the top sentences. Yeah. All right, cool. See you next week.